Once again, welcome back to the class of hyperbolic functions. Previously, we've studied trigonometric functions. So today I want to look at hyperbolic functions. From trigonometry, we notice that we have got a trigonometric ratio called tangent or tan of theta. We have got sine or sine of theta, and we have got cosine of theta. All these are trigonometric functions. All these are trigonometric. Similarly, from these trigonometrics, we also have hyperbolic functions corresponding to these trigonometric functions. We have got hyperbolic functions. So for tan, we have got tan, we call it tan, and we add hyperbolic of the same angle theta. And this one is read as tad. That is the sound of that tad of the angle theta. So this is the hyperbolic correspondent of tan. So the same way we have got sine of angle theta, we also have sine hyperbolic of the angle theta. Read as, this is the sound for this, we read it as sheath of the angle theta. The same way we have got cosine in trigonometry, we also have got cosine hyperbolic of an angle theta, read as cos. This is read as cos of an angle theta. From complex numbers, we realize that sine of theta, of an angle theta, can be equated, and the cosine also can be equated to some complex values as cosine to be equal to exponential of j theta plus exponential of negative j theta. All these multiplied by a half. And we also realize that sine of the angle can also be gotten as a half exponential of j theta minus exponential of j theta. So we can do manipulations to these constant complex variables and get that we have got a cosine and a sine of an angle. We found that cosine of an angle theta can be changed into hyperbolic as cosine of an angle theta using these complex conjugate terms as follows, such that cos hyperbolic of an angle theta is given as an exponential of theta plus exponential of negative theta over 2 as that, sorry, minus. And we also found that sheath theta, or the sine hyperbolic of an angle theta, is given by exponential of theta plus exponential of negative theta over 2. So cos is given as this one and sheath is given as this one. Same way we know that from trigonometry, tan of an angle theta is equal to sine of theta over cosine of the same angle theta. So the same thing applies in hyperbolic, that such that tan of theta is given as sheath of theta over cos of theta. So we can substitute this and this for us to get tan in terms of hyperbolic functions. That one shall be equal to sheath, that is exponential of theta minus exponential of negative theta over 2, this one divided by cos of theta, that is exponential of theta plus exponential of negative theta over 2. So we can multiply by the reciprocal such that we get exponential of theta minus exponential of negative theta over 2. If you multiply by the reciprocal of this one shall be 2 over exponential of theta plus exponential of negative theta. So this one shall give us that tan theta shall be equal to 2 and 2 cancels out. You end up with exponential of theta minus exponential of negative theta over exponential of theta plus exponential of negative theta as that. So this is our tan. Same way we have got sec of an angle theta is equal to 1 over cos of theta. This one also applies, that second hyperbolic read as sec of theta is given by 1 over cos of the angle theta. That is 1 over the inverse of cos theta. That one shall give us 2 over exponential of theta plus exponential of negative theta. That one is secant of the angle theta. What about, we also have again, from trigonometry, we also know that cosec of an angle theta is given by 1 over sine of theta. So in trigonometry, we also have what cosecant hyperbolic, read as cosec of theta, given by 1 over sec of theta. That is the inverse of this one, of that one shall be 2 over exponential of theta minus exponential of negative theta as our cosec. And we also know that tangent cot of theta is given as 1 over tan of theta. This is now trigonometry, from trigonometry. What about hyperbolic? Hyperbolic, the cotangent becomes cotangent hyperbolic, read as chord. That one is read as, the sound is chord of theta, is given as 1 over tan of theta. That is the cotangent hyperbolic of theta. That is the inverse of what we have found here. The inverse of this one, that one shall be exponential of theta minus exponential, so it here becomes plus exponential of negative theta over exponential of theta plus minus exponential of negative theta. This and that one are inverse. So from trigonometry, we proved the first trigonometric identity. From trigonometry, we said that cosine squared of theta plus sine squared of theta is equal to 1. That one is the first trigonometric identity. However, this one might not apply in terms of hyperbolic functions. This is a trigonometrical identity. For hyperbolic functions, we use what we call Osborne's rule. Osborne's rule, which said that provided we have got a square of, in that function, the positive sign changes to negative. So it implies that cosine hyperbolic square of theta minus sine square of theta should be equal to 1. That one is what Osborne's rule is telling us. Let's prove Osborne's rule now. That is cos squared theta minus sine squared theta is equal to 1. Is this one true? Let's bring. We know that cosine is cos is exponential of theta plus exponential of negative theta over 2. But it is squared, so we square this one. Then we minus sine. C squared, that is exponential of theta minus exponential of negative theta over 2. We also square this. And what will this one be equal to? So this is what we intend to prove. So let's square this part. This part shall be over 4. If you square 2, we get 4. Exponential of theta plus exponential of negative theta. If you square upper, you also write it twice. Exponential of theta plus exponential of negative theta over 4. Everything minus this side also 2 squared is 2 is 4. Then this side also square exponential of theta minus exponential of negative theta multiplied by the same thing, exponential of theta minus exponential of negative theta. So let's expand that bracket and see what we get. Let's expand the bracket and see the output if it's really going to prove the Osborne's rule right. If we expand that bracket, we find that this one times this one, then you add to that one. That will be exponential of 2 theta. From the power of indices, you just add the indices. Then this one times this one, you sum the indices, becomes exponential of 0 plus exponential of 0 plus exponential of negative 2 theta. Everything over 4 minus everything over 4 if you expand this bracket, it's going to become exponential of 2 theta. This one becomes, this one is minus exponential of 0, minus again exponential of 0. Then this one times the last one becomes plus exponential of negative 2 theta. So the denominator is the same, we can share the denominator, so it becomes everything over 4. This one becomes exponential of theta, of 2 theta. Exponential of 0 is 1, anything raised by 0 is 1, plus 1 plus 1 plus exponential of negative 2 theta. Then you come there, this negative term, this one becomes minus exponential of 2 theta. This one becomes plus 1 plus 1. Negative term, this one becomes negative exponential of negative 2 theta. So, if this one and this one cancels out, this and this cancels out, you end up with 1 plus 1 plus 1 plus 1. That one gives us 4 over 4, which is equal to 1. So, from we prove that, it therefore means that cosine squared theta minus sine squared theta is equal to 1. So this is our first hyperbolic identity. First hyperbolic identity. That's our first hyperbolic identity. So in our next session, we are going to prove the several types of hyperbolic identities and compare them with what you have in the trigonometry. So we shall stop there for now. You can practice with what is cosine squared theta plus sec squared theta as in trigonometry. What is this? You can practice with this one by expanding the exponential, then you do the multiplications. Thank you for now.